Calculation of area. One of the primary objects of land surveying is to determine the area of the tract surveyed and to determine the quantities of the earthwork. Surveying. As we all know, survey means calculation. The units of measurements of area in English units are square feet or acres, while in metric units the units are square meters or hectares. General methods of determining areas by computation based directly on field measurement that includes first by dividing the area in number of triangles, second by offsets of baseline, third by latitudes and departures, in that it includes double meridian distance and double parallel distance. The fourth one by coordinate. The second major computation is by computation based on measurements scaled from a map, and the third one is by mechanical method, usually by means of plane meter. So let's first talk about the areas computed by the subdivision into triangles. We have an irregular shape of the area. Divide the area into number of triangles. In this method, the area is divided into a number of triangles and the area of each triangle is calculated. The total area of the tract will then be equal to the sum of areas of individual triangles. Let us take this triangle. Let us take this area that I have divided into equal amount of triangles. There are 5 triangles in this particular area. The area of each triangle, as we know, is area is equal to 1/2 AB sine theta, where A and B are the sines, and if the third length is not given, then we will use this formula. When we know the length of the third side, we will use the Heron's formula. Area is equal to under root of S minus A, bracket close, S minus B, bracket S minus C, bracket close. This is Heron's formula, and we could calculate S is equal to half A with the sum of A, B and C. Offsets of baseline. Here we have 4 major outfs: mid-ordinate rule, average ordinate rule, trapezoidal rule, and Simpson's 1/3 rule. Now let's talk about mid-ordinate. This method is suitable for long narrow strips of land. The offsets are measured from the boundary to the baseline of a survey line at regular intervals. The method can also be applied to a plotted map from which the offsets of the line can be scaled off. The area may be calculated by the following rules. Area is equal to O1 plus O2 till On divided by N whole multiplied by capital L, where L stands for length of the baseline, small n, number of divisions, and D the distance between each division. Here you can see, like from 1 to 2, it's the division, the distance, and the number of divisions. Here we have n number of divisions, but it could be till 5, 4 or any. Average ordinate rule. This rule also assumes that boundaries between extremities of the ordinates are straight lines. The offsets are measured to each of the points of divisions of the baseline. The area is given by delta is equal to average ordinate into length of the baseline, which would be O0 plus O1 till On divided by N plus 1 whole bracket L, where O0 is equal to ordinate of one end, On is equal to ordinate of the other end. Next we have trapezoidal rule. This rule is based on as assumption that the figures are trapezoidals. The rule is more accurate than the previous two rules, which are approximate versions of trapezoidal rule. Here we divide the certain area into some parts. Like here we have 4 divisions. So let the delta 1 be O0 plus O1 by 2 whole multiplied by D. Similarly, delta 2 would be O1 plus O2 whole by 2 divided by, multiplied by D. Then the last n, the area of last trapezoid would be delta n is equal to O n minus 1 plus O n divided by 2 into D. And the total area would be delta is equal to delta 1 plus delta 2 plus delta 3 till delta n. Then we have Simpson's 1/3 rule. This rule assumes that the short length of the boundary between the ordinates are parabolic arcs. This method is more useful than the boundary line departs considerably from the straight line. The area between the line AB, here you can see the curve DVF may be considered to be equal to the area of trapezoid ABCD plus the area of the segment between the parabolic arc DFC and the corresponding chord DC. Here it is O0, O1, O2. Here, as we are talking about DFC, so arc D, F, and C. This is the arc DFC. The area of trapezoid ABCD would be O0 plus O2 divided by 2 whole multiplied by. Similarly, for DFC would be 2 by 3 into FH into AB. As you can see here, 2 by 3 bracket O1 minus O0 plus O2 by 2. Here we have like O2, O0 plus O2 by 2. Similarly, we would get O0 plus O2 by 2 minus O1 whole multiplied by 2D. And then we will add the same to the nth, On minus 1 into n. That will give us 2d by 3 On minus 2 plus O4 On minus 1 plus On. And when will we calculate the whole area, it would come in a certain series. Total area would be delta is equal to d by 3 bracket O0 plus On plus 4 O1 plus O3 till On minus 1 and plus 2 O2 plus till On minus 2. Here's the quick way to learn this formula. Here just add the first end and the second and the last end, and then multiply by 4 to the odd or to the all odd numbers, and then plus 2 and multiply 2 by all the even ordinates. Then you will get this formula more easy. Area by double meridian distances. This method is the most often used by computing the area of a closed transverse. This method is also known as DMD method. To calculate the area by this method, the latitudes and departures of each line of the transverse are calculated. The trans is then balanced. Here, let us use the area. Let us calculate the area by double meridian in this figure only. Let's see. The double meridian distance of a line is equal to the sum of the meridian distances of the two extremities. Okay. Like here, the double meridian distance, it is represented by the symbol M. I have represented it by symbol M. As you can see here, M1 is equal to M of A plus small m of B. Similarly, M2, M3 and M4 would be calculated. M2 is equal to M of B plus small m of C. That would give us D1 plus D2. That would be M1 plus D1 plus D2. Similarly, the M3, M of C plus M. small m of D. That will give us m2 plus d2 minus d3. Area by the coordinates. Here, let us see through this figure only. Let x1, y1, x2, y2, and x3, y3, and x4, y4 be the coordinates of the stations A, B, C, and D, respectively of a transverse ABCD. If A is the total area of the transverse, we would be having the total area would be area of small a plus b plus small b plus area of small b, capital C and small c minus area of small c, capital D, small d minus area of small d, capital D, capital A and small a. That would be half y1 minus y2 into x1 plus x2 plus y2 minus y3 into x2 plus x3 minus y4 minus y3 into x4 plus x3 minus y1 minus y4 x1 plus x4. If we would be generalizing this, we would get A is equal to half